the death of the universe, from the last star to eternal darkness. Look up tonight, and the universe appears permanent. The stars seem fixed. Galaxies turn so slowly that no human eye can see them move. The darkness between them feels like an empty stage on which the same lights will burn forever. But the sky is not a painting. It is a process. Every star is consuming a limited supply of fuel. Every galaxy is changing. Every orbit is being disturbed. Space itself is expanding, carrying most distant galaxies farther away from one another. And if the laws of physics continue to operate as our best models suggest, the universe has a future so long that the age of the cosmos today is almost nothing beside it. There will be a last ordinary star. There may be a last explosion. There may be a final black hole. And beyond all of them lies a state in which energy remains. Particles may still move, and time may still exist. But almost nothing useful can happen. No new stars, no warm worlds, no chemistry sustained by sunlight, no great differences between hot and cold from which complexity can draw power. This ending is often called the heat death of the universe. But heat death is only one possible future, and even that story contains deep uncertainties. Dark energy may not be constant. Protons may or may not decay. Black hole evaporation has never been observed. And a controversial new calculation published in 2025 suggests that some stellar remnants might disappear far sooner than older estimates predicted. So this is not a prophecy. It is a journey through the best scientific picture we have. From the death of the sun, to the final red dwarfs, to black dwarfs, black holes, cosmic horizons, quantum uncertainty, and the last usable energy in the cosmos. This is the complete story of how the universe may end. What does it mean for a universe to die? Before traveling into the far future, we need to be precise about what the death of the universe actually means. The universe is not a living organism. It does not have a heartbeat that simply stops. And the most likely ending is not a moment when every particle suddenly vanishes. Instead, physicists usually describe the ending in terms of usable energy. Almost everything interesting happens because something is different from something else. A star is hot while surrounding space is cold. That temperature difference allows energy to flow outward as light. A waterfall begins high and ends low. The difference in height allows gravity to do work. A battery has separated charges. Connect them, and the difference drives an electric current. Life also depends on gradients. Earth receives concentrated energy from the sun and releases lower temperature radiation into space. Living systems use that flow to maintain structure, grow, repair themselves, and reproduce. When energy becomes evenly distributed, it has not necessarily disappeared, but it becomes less available for doing organized work. This is where entropy enters the story. The second law of thermodynamics says that in an isolated system, total entropy does not spontaneously decrease. In everyday language, energy tends to spread out, and arrangements that are highly ordered tend to become less special with time. Coffee cools because its thermal energy spreads into the room. A flame dies because concentrated chemical energy is converted into dispersed heat and radiation. Gas released into a room spreads through the available volume. It does not naturally gather itself back into one corner. Gravity complicates the picture because it can create local structure. Diffuse gas can collapse into stars. Stars can gather into galaxies. A cloud becoming a star looks like increasing order. but the collapse releases heat and radiation into the surrounding universe. The total entropy still rises. Black holes take this to an extreme. They are among the highest entropy objects known for a given region of space. So cosmic evolution is not simply everything becoming messy. It is a continual conversion of concentrated, useful energy into more dispersed forms, even while gravity temporarily builds spectacular islands of structure. Heat death would occur when the universe approaches thermodynamic equilibrium. No large accessible energy differences remain to power complex processes. Particles would not necessarily be perfectly motionless. Photons might still travel. Quantum fields would still exist. Depending on the true nature of dark energy, the far future could retain an extremely low horizon temperature. But without meaningful gradients, there would be almost no opportunity to extract work, build new structures, or sustain observers. There is another important warning. When we project the universe forward by trillions, quintillions, or vastly more years, we are extending known laws far beyond the range where they have been directly tested. General relativity describes gravity extraordinarily well. Quantum field theory describes particles with astonishing accuracy. But we do not yet possess a complete experimentally verified theory that unifies gravity with quantum mechanics. We do not know whether the proton is absolutely stable. We do not know the identity of dark matter. We do not know what dark energy is or whether it changes over time. And in 2025, the Dark Energy Spectroscopic Instrument reported stronger hints, not a discovery, that dark energy may evolve. If that hint survives future tests, the final fate of the universe may be different from the simplest heat-death picture. Everything that follows must therefore be understood as a branching map. Some paths are strongly supported, some depend on assumptions, and some are speculative possibilities included, because a complete account should show where established physics ends and uncertainty begins. The end of Earth and the Sun. The death of the universe begins, from our perspective, with a much smaller ending. The Sun is about 4.5 billion years old. It is roughly halfway through its stable main sequence lifetime, converting hydrogen into helium in its core. But the Sun is not remaining perfectly constant. As helium accumulates in the core contracts and heats, causing the Sun's luminosity to increase gradually. Long before the Sun becomes a red giant, Earth is expected to become increasingly hostile to complex surface life. Estimates depend on climate feedbacks and biological assumptions, but over roughly the next billion years, rising solar brightness may drive the planet toward conditions in which oceans are lost and the familiar biosphere cannot continue. Around 5 to 6 billion years from now, the Sun will exhaust the hydrogen fuel in its core. The core will contract. The outer layers will expand enormously. The Sun will become a red giant. Mercury and Venus are expected to be engulfed. Earth will certainly be sterilized and may also be swallowed, although the precise outcome depends on a competition between the expanding solar atmosphere, tidal forces, and the widening of Earth's orbit as the Sun loses mass. Either way, the present Earth will not survive as a living world. During later stages, the Sun will ignite helium in its core for a comparatively brief period. It will then shed its outer layers into space, creating a glowing planetary nebula. The exposed core will remain as a white dwarf, an object about the size of Earth containing a large fraction of the Sun's original mass. A white dwarf is not powered by ongoing nuclear fusion. It shines because it begins extremely hot and slowly releases stored thermal energy. Over immense time, it cools and fades. The sun's death will not be unique. Stars follow different endings based largely on mass. Massive stars burn through fuel rapidly, living only millions of years before exploding as core collapse, supernovae, or collapsing more quietly. They may leave neutron stars or black holes. Sun-like stars shed their outer layers and become white dwarfs. The smallest true stars, red dwarfs, are different. They mix their fuel efficiently and consume it very slowly. Some may shine for trillions of years. That means the universe's future is not immediately dark after stars like the sun disappear. The bright, short-lived stars die first, then the medium-sized stars. At last, the cosmos becomes dominated by dim red points, each one burning with extraordinary patience. Planetary systems will also change. When stars lose mass, planetary orbits can expand. Some planets may survive as frozen worlds around white dwarfs. Others may be destabilized by passing stars, galactic encounters, or the deaths of their host systems. In binary systems, stellar remnants may continue to exchange matter, merge, and occasionally produce novae, supernovae, or gravitational waves long after ordinary star formation has declined. The early chapters of cosmic death are therefore not quiet. They are filled with red giants, supernovae, planetary destruction, white dwarfs, neutron star collisions, and black hole mergers. The universe does not simply turn off. It flickers, rearranges itself, and gradually spends its remaining fuel. Galaxies become islands. While stars age, the universe itself continues to expand. The expansion is not like galaxies flying through a pre-existing empty container. On the larger scales, the distance between gravitationally unbound regions grows because space itself expands. Nearby systems held together by gravity do not simply stretch apart with the universe. The solar system remains bound. The Milky Way remains bound. The galaxies of the local group are also expected to remain gravitationally connected. But more distant galaxy groups and clusters are carried away by the accelerated expansion. If dark energy behaves approximately like a cosmological constant, then after roughly 100 billion years, nearly every galaxy not gravitationally bound to our local group will have faded beyond our accessible cosmic horizon. They will not appear to cross a visible wall. Their light will become increasingly redshifted and weakened until it is effectively undetectable. The cosmic microwave background, the ancient afterglow of the hot early universe, will also be stretched to longer wavelengths and eventually hidden below the plasma frequency of interstellar material. Future astronomers may be unable to detect it. The evidence that now reveals cosmic expansion, dark energy, and the Big Bang could disappear. Observers living in that remote era might see only one enormous gravitationally bound collection of stars and remnants surrounded by darkness. For years, popular accounts confidently predicted that the Milky Way and Andromeda would collide in about 4 to 5 billion years and merge into a giant elliptical galaxy. More recent calculations have highlighted greater uncertainty. The motions and masses of Andromeda, the Triangulum Galaxy, the Large Magellanic Cloud, and other local group members make the exact next 10 billion years difficult to predict. A direct Milky Way-Andromeda merger on the classic timetable is no longer treated as guaranteed, but the larger point survives. The local group is expected to remain bound while unbound galaxies disappear from view. Over much longer periods, interactions within the group will continue to rearrange its members. Stars will be scattered. Central black holes may merge. The final system will become an isolated island in an expanding sea. This creates one of the strangest consequences of cosmic acceleration. The universe may become less knowable with time. Today, we can observe distant galaxies at many stages of development. We can measure the expansion of space. We can detect the microwave background. We can study primordial light elements and reconstruct the early universe. Far future astronomers may inherit more advanced technology, but less evidence. They might reasonably conclude that their island is the entire cosmos. The galaxies beyond it will still exist in the global universe, but no signal emitted after a certain point will ever reach the island. Causally, those regions are gone. This is not the destruction of galaxies. It is the destruction of contact. The visible universe shrinks, not because space becomes smaller, but because accelerated expansion removes most of reality from communication. Before the last stars die, cosmology itself may become impossible. The last stars. The present universe is still capable of making stars. Cold clouds of molecular gas collapse, fragment and ignite. Stellar winds and supernovae can compress nearby material and trigger new generations. Galaxies collide and funnel gas into dense regions where star formation accelerates. But every generation changes the inventory. Some gas is locked inside long-lived stars and remnants. Some is heated or expelled from galaxies. Heavy elements accumulate. Black holes consume a fraction. The available cold gas becomes harder to gather into new stars. Star formation has already declined dramatically from its cosmic peak billions of years ago. In the far future, it will become increasingly rare. Exact timelines depend on how efficiently gas is recycled and how galaxies evolve. But classic long-term models place the effective end of conventional star formation somewhere between about 1 trillion and 100 trillion years from now. There may still be occasional new stars created after that through unusual events, collisions between brown dwarfs, mergers of low-mass objects, or rare gravitational encounters. So, the last star is not a sharply scheduled appointment. It is the fading tail of a process. The stars that dominate the final luminous age will be red dwarfs. They are far smaller and dimmer than the Sun. Because their interiors can circulate material efficiently, they are able to access a much larger fraction of their hydrogen fuel than stars like ours. A low-mass red dwarf may remain stable for trillions of years. During that time, galaxies will look very different. Brilliant blue stars will be absent. Sun-like yellow stars will be gone. Supernovae will become rare. The night will be ruled by faint crimson points. Some red dwarfs may slowly grow hotter and bluer near the ends of their lives, rather than swelling into red giants like the Sun. Their evolution is theoretical because the universe is not yet old enough for even one low-mass red dwarf to have completed its full life cycle. Eventually, the final red dwarfs will exhaust their hydrogen. They will leave white dwarf-like remnants, sometimes called helium white dwarfs or blue dwarfs, during transitional phases, depending on the model. Afterward, the universe enters what long-term cosmologists call the degenerate era. The word degenerate here does not mean damaged or inferior. It refers to quantum degeneracy pressure, the effect that supports white dwarfs and neutron stars against gravity. The main surviving objects will be white dwarfs, cooling stellar cores supported by electron degeneracy pressure, neutron stars, ultra-dense remnants supported by neutron degeneracy pressure and nuclear interactions, brown dwarfs, objects too small to sustain ordinary hydrogen fusion, planets, moons, asteroids, and frozen debris. black holes of many masses, and perhaps dark matter structures whose true nature remains unknown. The universe will still contain matter, but it will no longer contain a normal stellar population. Light will come from rare collisions, radioactive decay, accretion events, mergers, and the slow cooling of ancient remnants. There may be extremely long-lived sources of low-level energy. A civilization with unimaginable engineering could, in principle, extract power from rotating black holes, accretion, particle decay, or the controlled merging of compact objects. But the natural cosmos will be growing darker. After perhaps 100 trillion years, the great age of starlight is effectively over. Everything humanity has ever seen in the night sky belongs to an early and temporary phase. The degenerate era, cold stars, lost planets, and gravitational ruins. Once conventional stars are gone, gravity continues working. Galaxies are not perfectly stable machines. They are large collections of objects repeatedly passing one another. Most encounters are distant, but over enormous spans of time, small gravitational changes accumulate. A star or remnant can gain energy in one encounter and lose it in another. Some objects sink toward the galactic center. Others are accelerated outward. Over roughly 10 to the 19th or 10 to the 20th years in classic estimates, many galactic systems gradually evaporate through gravitational scattering. This is not evaporation in the thermal sense. It means objects are ejected one by one until much of the galaxy disperses. A minority of remnants may fall into central black holes. Others may merge through gravitational wave emission. Many will become isolated, separated by distances that continue to grow with cosmic expansion. Planetary systems face the same long erosion. Passing remnants can disrupt orbits. Multi-planet systems can become chaotic. Some planets collide with their dead stars. Others are thrown into interstellar space. Eventually, most surviving worlds may become rogue planets, frozen, dark, and hostless. A white dwarf begins hot, but without fusion, it gradually cools. At first it glows visibly. Later, it radiates mostly infrared. Its interior crystallizes. Given enough time, it approaches the temperature of its environment. A fully cooled white dwarf is often called a black dwarf. No black dwarfs exist today because the universe is far too young. Even the oldest white dwarfs have not had enough time to cool completely. Black dwarfs are therefore predictions, relics of a future no telescope can currently observe. Neutron stars will also cool, although they are more complicated. Their crusts and cores contain matter at densities beyond anything found naturally on Earth. Over long times, they may undergo magnetic decay, interactions with dark matter, collisions, or hypothetical particle decay processes. Brown dwarfs and giant planets can collide. Two brown dwarfs that merge with enough combined mass might ignite hydrogen and create a new, unusually late star. Such events would become rarer as the galaxy disperses, but they prevent the transition into darkness from being perfectly clean. The late universe may be punctuated by isolated sparks separated by absurd intervals. A collision after a quadrillion years. A merger after a quintillion. A planet torn apart by a black hole after an even longer silence. The natural meaning of event changes when the wait between events exceeds the entire current age of the universe by billions of times. Dark matter could also matter enormously. If dark matter particles are their own antiparticles, they might annihilate slowly, producing radiation over long periods. If they decay, their decay products could alter the evolution of halos and remnants. If dark matter consists partly of primordial black holes, the future changes again. But because the identity of dark matter remains unknown, the dark matter chapter of cosmic history cannot yet be written with confidence. What is clear is that visible matter becomes progressively colder, more isolated, and more gravitationally processed. The universe shifts from a place dominated by burning stars to a place dominated by leftovers. Does matter itself decay? At this point, the future divides around one of the deepest unanswered questions in particle physics. Is the proton stable? Protons are central components of atomic nuclei. Ordinary matter, rocks, oceans, planets, stars, and human bodies depends on them. The standard model of particle physics treats the proton as stable, but many proposed grand unified theories predict that protons can decay into lighter particles after an extraordinarily long average lifetime. Experiments such as Super Kamiokande have searched for proton decay and found no confirmed event. For one important decay channel, the lower limit on the proton's partial lifetime is greater than roughly 2.4 times 10 to the 34 years. That does not prove eternal stability. It means that if protons decay through that channel, they do so very rarely. If proton decay occurs on timescales, such as 10 to the 34 through 10 to the 40th years, then white dwarfs, neutron star matter, planets, and other baryonic remnants would gradually lose mass. A black dwarf would not remain a black dwarf forever. Its protons and bound neutrons would decay, converting the remnant into lighter particles and radiation. Matter would thin away. A planet-sized object might spend eons releasing tiny amounts of energy from individual decay events before finally becoming a diffuse cloud of particles. In that branch of the future, black holes eventually become the dominant large structures because ordinary baryonic remnants disappear first. But if the proton is absolutely stable, another path opens. Black dwarfs could survive for vastly longer. Quantum tunneling may allow nuclei in their crystallized interiors to fuse even at temperatures near absolute zero. Over times that cannot be represented meaningfully in ordinary language, matter could gradually be processed toward iron group nuclei. In a 2020 study, astrophysicist Matt Kaplan examined the possibility that the most massive black dwarfs could eventually become unstable and collapse in black dwarf supernovae. The first of these events in that model might occur after about 10 to the 1100 years. That is a 1 followed by 1100 zeros. For comparison, the present age of the universe is about 1.4 times 10 to the 10 years. These hypothetical explosions would occur only if several assumptions are correct. Protons must remain stable, black dwarfs must survive other decay channels, and pycnonuclear fusion must proceed as modelled. If so, they could be among the last spectacular nuclear events in the universe. Imagine a cosmos that has been dark for an interval so long that the full history of stars is effectively zero beside it. Then, in one isolated region, a black dwarf collapses. For a brief moment, the darkness contains an explosion. No nearby observer is likely to see it. Accelerated expansion would have carried other remnants beyond causal contact. Each event would occur alone, in its own horizon volume. The far future depends not only on astronomy, but on the hidden stability of matter itself. The age of black holes. Whether ordinary matter decays quickly by far future standards or survives through black dwarf evolution, black holes are expected to become increasingly important. They are created by stellar collapse, mergers, and the growth of galactic centers. Over cosmic time, black holes can merge into larger black holes. But black holes do not simply begin evaporating immediately. A black hole has a temperature, the Hawking temperature, that decreases as its mass increases. Astrophysical black holes today are colder than the cosmic microwave background. They absorb more energy from their surroundings than they emit through Hawking radiation. Only after the universe cools sufficiently will they enter a phase of net evaporation. For stellar mass black holes, this transition may require hundreds of billions of years or more, depending on the environment and cosmological model. In 1974, Stephen Hawking showed that quantum fields around an event horizon cause a black hole to emit thermal radiation. The common popular image describes particle pairs forming at the horizon, with one falling in and one escaping. That picture can be useful, but it is not the full derivation. Hawking radiation arises from the behavior of quantum fields in curved spacetime and from how different observers define particles. The result is extraordinary. A black hole can lose energy. Because energy and mass are equivalent, it can lose mass. And because smaller black holes are hotter, evaporation accelerates as the black hole shrinks. The lifetime scales approximately with the cube of the black hole's mass. A non-rotating black hole with the mass of the Sun has a standard semi-classical evaporation time of roughly 2 × 10 to the 67 years. A black hole several times the Sun's mass lasts longer. A supermassive black hole with millions or billions of solar masses can survive to around 10 to the 85, 10 to the 90, or even beyond, depending on its mass. The largest black holes conceivable after repeated mergers may endure close to 10 to the 100 years or longer. These numbers are estimates within semi-classical physics. Rotation, charge, particle species, accretion history, and unknown quantum gravity effects can change the details. As a black hole evaporates, it grows hotter and brighter. Near the end, the semi-classical calculation predicts rapid energy release. But the final Planck scale stage is exactly where our present theories become incomplete. The black hole may end in a high-energy burst. It may leave a stable or long-lived remnant. Information may be encoded in subtle correlations within the radiation. Or quantum gravity may produce an outcome no current model captures. So the phrase, "the final black hole explodes," should never be presented as experimentally settled fact. What we can say is that Hawking's calculations strongly suggest black holes are not eternal. Within standard semi-classical physics, across an almost empty universe, one black hole after another would radiate away. The smallest go first. The giants remain. For ages beyond imagination, they would be the darkest monuments in existence. Then they too would fade. If the standard picture is correct, the universe would pass from the black hole era into a still emptier state dominated by extremely low energy radiation, light particles, and whatever stable species nature permits. The 2025 calculation that changed one possible timeline. In 2025, a striking headline spread across Science News. The universe may decay much sooner than previously thought. The calculation came from Heino Falke, Michael Wondrak, and Walter van Zwijlekom of Radboud University. Their published work explored a proposed process called gravitational pair production. In earlier research, the authors argued that curved spacetime might create particles without requiring a traditional black hole event horizon. They then applied the framework to compact stellar remnants, including neutron stars and white dwarfs. In their model, the evaporation timescale depends strongly on average density. They estimated a maximum age of roughly 10 to the 68 years for neutron stars. comparable in order of magnitude to stellar black hole lifetimes in their framework, and about 10 to the 78 years for the longest-lived white dwarfs. That is dramatically shorter than the 10 to the 1100-year timescale associated with some proton-stable black dwarf scenarios. The researchers also calculated playful examples, including a lifetime of roughly 10 to the 90 years for a human body placed in an otherwise empty universe under the assumptions of the model. But this result must be presented carefully. It is not an observed decay. It is not the confirmed date of the universe's end. And it does not mean the whole universe disappears simultaneously after 10 to the 78 years. It is an upper limit calculation for particular objects under a specific theoretical mechanism. More importantly, the underlying gravitational pair production interpretation has been debated in the scientific literature. Other physicists have published critiques arguing that some claims conflict with established exact results in related quantum field settings. The original authors have responded that the critiques apply their formula outside its intended domain. This is how theoretical physics often advances. A new framework makes a surprising prediction. Other researchers test the assumptions, search for inconsistencies, and propose alternatives. The disagreement is not a flaw in science. It is the process by which untested ideas are strengthened, revised, or rejected. For this documentary, the responsible conclusion is simple. The 2025 work offers an intriguing possible upper limit on the survival of stellar remnants. It may profoundly shorten one branch of the cosmic timeline, but it is not yet part of the same secure foundation as stellar evolution, cosmic expansion, or the observed existence of white dwarfs and black holes. The far future remains open to new physics. Heat death, when nothing useful remains. After the last stars, the last remnants, and perhaps the last black holes, what remains? The simplest answer is not nothing. It is an almost empty universe containing extremely dilute radiation, neutrinos, electrons, positrons, perhaps stable dark matter particles, and whatever else can't decay. Space continues expanding. Wavelengths stretch. Densities fall. Interactions become increasingly rare. Heat death is the approach toward maximum entropy under the available conditions. The important word is approach. In an eternally expanding universe, perfect equilibrium across unlimited space may never be reached in a simple global sense. Cosmological horizons divide regions that can no longer communicate. Quantum fields and dark energy complicate the definition of a final equilibrium. Yet locally, usable free energy can become vanishingly scarce. No hot star shines into cold space. No dense gas cloud collapses. No chemical reservoir waits to be tapped. No rotating structure remains conveniently available to power machines. Particles may still have motion, but random motion by itself is not enough. To extract work, a system needs a difference: hot and cold, high and low pressure, separated charge, concentrated matter, ordered fuel. Heat death is the loss of those differences. Time does not necessarily stop. General relativity may still define intervals. Quantum events may still occur. Photons may continue traveling. But there may be no durable clocks, no repeating natural structures, and no observers to count the passage. A second, a trillion years, and a number of years with a trillion zeros would all pass without stars, seasons, heartbeats, or orbital cycles to distinguish them. In a universe dominated forever by a true cosmological constant, empty space possesses a cosmic horizon and an associated extremely low temperature. This de Sitter-like state is not absolute zero. Quantum fluctuations may occur, but whether those fluctuations can create lasting complex structures, and how probabilities should be interpreted over infinite time, is deeply controversial. Popular discussions sometimes mention Boltzmann brains, hypothetical self-aware fluctuations arising by chance in an equilibrium universe. The concept highlights a serious puzzle in cosmology, but it should not be treated as a predicted population waiting in the future. Its relevance depends on how cosmological measures, vacuum decay, and observer probabilities are defined. The honest picture is austere enough without exaggeration. The universe may expand into a state where almost every particle is causally isolated from almost every other, where usable energy is effectively gone, and where no natural process reconstructs the complexity once produced by stars. The cosmos is not destroyed in one dramatic moment. It becomes unable to continue the kind of history we recognize. That is heat death. Other possible endings. Heat death is the leading long-term outcome if cosmic expansion continues and dark energy behaves approximately like a constant. But it is not the only scientifically discussed ending. The first alternative is the Big Rip. If dark energy has an equation of state more extreme than a cosmological constant, a hypothetical form often called phantom energy, its density could increase as the universe expands. Expansion would eventually overcome structures on progressively smaller scales. Galaxy clusters would become unbound, then galaxies, then planetary systems. Closer to the end, planets, molecules, and even atoms could be torn apart. The Big Rip is not currently established. It depends on a specific behavior of dark energy that observations have not confirmed. The second alternative is a Big Crunch. If the expansion of the universe were to slow, stop, and reverse, matter and radiation could collapse toward a hot, dense state. In the simplest current model with positive dark energy, a future recollapse is not favored. But evolving dark energy or new gravitational physics could change the conclusion. Some speculative cosmologies replace the final crunch with a bounce, beginning another expanding phase. These models are active theoretical research, not established descriptions of our future. The third alternative is vacuum decay. Measurements of the Higgs boson and top quark suggest, within the standard model and current uncertainties, that our electroweak vacuum may be metastable rather than absolutely stable. A metastable vacuum can persist for a time vastly longer than the present age of the universe, yet still have a non-zero probability of tunneling to a lower energy state. If a true vacuum bubble formed, it could expand at close to the speed of light. Inside it, the values of fields and perhaps the effective laws governing particles could differ. Structures like atoms might be impossible. No warning could arrive before the bubble because no signal can outrun it. However, the vacuum lifetime depends sensitively on particle masses, unknown high-energy physics, gravity, and conditions in the early universe. The fact that our observable universe has survived for 13.8 billion years already constrains dangerous possibilities. Vacuum decay is a serious concept in quantum field theory, but it is not a reason to expect sudden destruction on any human timescale. Other proposals include cyclic universes, changes in fundamental constants, stable black hole remnants, transitions to new phases of spacetime, or physics beyond the standard model that completely rewrites the far future timeline. A complete documentary must include these possibilities, but must not pretend they are equally likely. Heat death follows most directly from the standard cosmological model with continuing accelerated expansion. The Big Rip requires a particular evolving form of dark energy. The Big Crunch requires expansion to reverse. Vacuum decay depends on quantum field stability and unknown high-energy physics. The universe's ending is not one answer. It is a test of everything we still do not understand. Dark energy may not be constant. At the center of the uncertainty is dark energy. Observations show that the expansion of the universe is accelerating. The simplest explanation is a cosmological constant, a fixed energy density associated with empty space. In that model, accelerated expansion continues forever. Distant galaxies disappear beyond horizons. Matter becomes isolated. The universe approaches a cold, de Sitter-like future. But scientists do not know whether the cosmological constant is truly the answer. Dark energy accounts for roughly 2/3 of the present cosmic energy budget. Yet its physical nature is unknown. In March 2025, the Dark Energy Spectroscopic Instrument released results from its first 3 years of data. When DESI measurements were combined with some cosmic microwave background, supernova, and weak lensing datasets, the evidence hinting that dark energy may evolve became stronger than in the first-year analysis. The statistical significance depended on which datasets were combined. It did not reach the standard required for a discovery. The result may weaken with better data. It may reveal an unrecognized systematic effect, or it may be the first sign that the simplest cosmological model is incomplete. DESI completed its planned 5-year map in 2026 and continues to explore the universe, while other projects, including the Euclid mission, the Vera C. Rubin Observatory, and NASA's Roman Space Telescope, are designed to improve measurements of cosmic expansion and structure. If dark energy changes with time, the distant future could differ radically from the classic heat-death timeline. It might weaken, allowing gravity to matter more. It might change sign, opening paths toward recollapse. It might strengthen, making a big rip possible. Or its evolution might settle into another form of eternal expansion. This is why no responsible scientist can provide a final countdown clock for the universe. We know the cosmos is changing. We know stars have finite lives. We know usable energy tends to disperse. But the force shaping the largest scales of the future remains unidentified. The ending is written in a language we have not yet fully learned to read. What the end of the universe means for us. The far future can feel oppressive. Every star goes dark. Every familiar galaxy disappears. Every monument breaks down. Even black holes may fade. But scale changes meaning. The universe is about 13.8 billion years old. The age of starlight may continue for tens of trillions of years. We live astonishingly early in the possible history of the cosmos. Most of the future is not our future in any practical sense. Humanity faces challenges measured in years, centuries, and perhaps millennia, not 10 to the 67 years. The death of the universe does not reduce the value of anything happening now. A song is not worthless because it ends. A life is not meaningless because it is finite. A star is not less beautiful because it consumes its fuel. Finitude can create value by making moments unrepeatable. And our moment is unusual. We live while distant galaxies remain visible. We can measure the expansion of space. We can detect the afterglow of the Big Bang. We can observe stars being born and stars dying. We can discover that the iron in blood and the calcium in bone were assembled through cosmic processes, while remembering that much of the hydrogen in our bodies is older than the stars themselves, forged in the early universe. We are not simply made from stars. We are made from the entire history of the cosmos. Primordial hydrogen, stellar carbon and oxygen, supernova products, neutron star elements, planetary chemistry, and biological evolution. For a brief interval, matter became capable of asking where it came from and where everything is going. The universe may one day become dark beyond recovery, but it is not dark now. The stars are burning now. Galaxies are visible now. Questions can be asked now. And every answer we find preserves something that the far future may no longer be able to discover. We are living not near the end, but near the beginning of the luminous age. The final darkness, if it comes, is almost infinitely far away. Tonight, the universe is still full of light. Not tonight. One day, the final ordinary star will fade. One day, the last isolated remnants may decay, collapse, or disappear through processes no living observer has ever witnessed. One day, the final black hole may release its last energy into a universe already ancient beyond comprehension. And if heat death is the destination, the cosmos will continue expanding with almost no usable difference left to drive change. But not tonight. Tonight, sunlight reaches Earth. Stars ignite inside clouds of gas. Planets circle distant suns. Galaxies shine across billions of light years, carrying messages from the past into our telescopes. We are here early enough to see them, early enough to understand that they will not last, and early enough to appreciate what it means that they exist at all. The universe is not dead. It is not close to dying. It is only beginning a story whose final pages may be written in darkness.